Materials Innovation Fund. I also would like to extend my welcome to our visiting delegation. It's an honor to be able to present our work for you too. So the Critical Materials Innovation Hub is a public-private consortium funded by the Department of Energy's Advanced Materials and Manufacturing Technologies Office. And I'll talk a little bit more about our mission as we get into the presentation. But you can see that we are clearly a mixture of many different organizations operating under kind of one roof, be it a virtual roof. But basically, we're 9 national laboratories, 20 academic institutions, and 28 private sector companies. And our general mission is to address criticality of materials needed for energy technologies. And we'll talk a little bit more about how we define criticality. Before I go into that, I just wanted to introduce you to the Ames National Laboratory. Our origin began, as you can kind of see, back just prior to the start of World War II and the Manhattan Project. Actually, it started with a supply chain problem. Back then, in the late 30s, there was a lot of theory predictions about fission. Can we split the uranium atom? And to be honest, to build the first nuclear reactor, to demonstrate fission, required a large quantity of high purity uranium. In the late 30s, no such thing existed. At best, you might find maybe a cubic centimeter of high purity uranium. And so Enrico Fermi approached these two gentlemen. To the left is Frank Spedding, and to the right is Harley Wilhelm. And they were researchers at the Iowa State College, and in particular, they did the lanthanides, the rare earths. And so they were asked, could they devote some attention to uranium, producing highly purified uranium for the demonstration of fission? And they took on that challenge. And in fact, they were able to do that with a relatively simple process using magnesium as a reductant to reduce uranium fluoride. They went on to produce over 2 million pounds of uranium in the little shack there that we called Little Ankeny, because Ankeny is a city near Ames, Iowa. It was a munitions facility. And so as a result, the uranium was not only used for the first pile reactor, but in fact went on to be shipped to Oak Ridge to be part of the Manhattan Project. So we're very proud of that. And they got the first, and I think only university to receive this Army-Navy flag, which was for production for the Second World War effort. So that's kind of our origin story. We are one of 17 national laboratories that are overseen by the Department of Energy. You may recognize many of these: Idaho National Laboratory for sure, Los Alamos, and Ames. Ames sits in the center of Iowa, and we're an Office of Science laboratory. So traditionally, we've done basic energy science or discovery science work. A lot of that work focused on rare earths, and so one of our specialties has been rare earth metals. We are the only national laboratory that actually sits on the campus of a major university, in this case, Iowa State University. Looking at this picture, you probably can't pick out our buildings because there are no guards, there are no gates, and most importantly, there are no guns. And so we have a very open, collaborative atmosphere that's both academic oriented and mission driven, as most of the national laboratories are. So we have kind of the best of both worlds. All right. So let me start with this question: what are critical materials? Maybe you've heard this before, but critical materials actually depends on who you are, where you are, and when you are. And so who is shown here, who we are, we're the Department of Energy. So the critical materials we worry about are those that are important for energy technology. So these two figures basically display an analysis of how important the particular elements or materials are to energy. That's the vertical axis. The x-axis displays supply risk, or the risk of a disruption to the ability to get those materials. So the importance to energy can be measured in lots of different ways. One way would be to measure the ability for those materials to abate carbon or greenhouse gas emissions. Another factor might be, are there substitutes? So instead of dysprosium, can I use something else? And if that's the case, well, it's not so important. So that's how we do the vertical axis. And the supply risk is also several factors, but the most important factor that goes into this particular analysis is geographical concentration. So the majority of these materials that are in yellow and red, the supply chain flows through one or just a handful of countries. And so that's who we are. When we are is short-term versus medium-term. If you happen to be aware, China has done two things to restrict exports of materials. In December, they restricted gallium and germanium, antimony, and hard materials. And in January, in response to tariffs, they've restricted tungsten and tellurium and indium. And so here we are. Short term, what do? You no longer can buy it. What do companies do? So that's one consideration. Medium term, actually, the goal there is to look 5 years out and say, what options do we have to mitigate the risk of a supply chain disruption? And that's really where the Critical Materials Innovation Hub comes in, because we're able to affect the medium term by developing new technologies. So I did who we are and when we are and where we are. So not every country has all of these materials as natural resources. The US certainly has rare earth. In fact, we are now the second largest producer of rare earths in the world. China is first, we are second, Australia is third. And so that's good. However, we don't process the rare earths. We can dig them out of the ground and we can ship them to China to be processed. But we have resources. That's good. Cobalt nickel, we have one operating mine scheduled to be closed in 2028 in the Upper Peninsula of Michigan, and that's it. We have no other mines. You have a cobalt mine, but prices are depressed and it's been halted. So where you are makes a difference. Canada has nickel and cobalt. They don't necessarily think nickel and cobalt are critical because they have the mines, they have the processing. So that's how we define critical materials. And for energy, they can be classified into this grouping. So the first, neodymium, praseodymium, dysprosium, and terbium are rare earths elements that are important for permanent magnets. Permanent magnet motors and generators are the most efficient for translating into mechanical motion or conversion to electrical energy from mechanical motion. The next group is, I thought I corrected that, is energy storage material. And I thought I removed the second, graphite, but okay, graphite's really, really important, so we list it twice. Iridium and platinum, kind of looking forward to a hydrogen economy. So iridium is used in electrolyzers and platinum for fuel cells. Gallium and silicon carbide for LEDs and power electronics for your electric vehicles. Magnesium and aluminum are lightweight metals and alloys for building your vehicles. So that's important for transportation. Of course, we know silicon for solar panels. They are also, silicon is an alloying element for aluminum, so lightweight alloys and electrical steel, important for permanent magnet motors, and then copper and electrical steel. So those are the ones that the Department of Energy worries about. And we worry about a subset. We worry about the first four groupings in the Critical Materials Institute. So no matter what we think about the growth for energy, it's going, the world is growing. The middle class is growing in every country. We are going to need more and more energy. So pretty easy projections that have been done. The sustainable development scenario in the center of the graph on the left suggests that we need 4 times the amount of energy. The demand for energy will grow 4 times in the next, I believe it was till 2040. And then a net zero scenario by 2050 will require 6 times the energy generation. That translates into materials because we need materials for power generation. And so you can make these projections 42 times the current capacity. I think it was 2020 annual capacity. For lithium, we would need 42 times the capacity. And graphite, cobalt, nickel, just 7 times for the rare earths, but clearly the demand for these materials will grow over the next 10 to 15 years. So the US strategy, how do we solve this problem? How do we get these materials? We think to be able to do that domestically, innovation is the key. We need to be able to increase our domestic supply of critical materials, to be able to diversify and unlock new sources. We need to increase the efficiency of how we use these materials. We can no longer just take our waste and throw it in landfills. And so can we improve the ability to use these materials efficiently? Can we manufacture our devices efficiently to minimize waste? And most importantly, can we do that while decreasing some of the environmental impacts and the health and safety of the workers, both in mining and manufacturing? And then finally, we really want to be able to not develop materials, processes, new processes that actually can be developed and deployed by industry. And that leads us to CMI, which is charged with developing the ecosystem. When we started in 2013, there was very little supply chain. So there was maybe 1 or 2 companies that had interest. A lot of companies use these materials, but they're not upstream. They tend to be OEMs, car makers and whatnot. And they see supply chain as a logistical problem as opposed to a demand problem. So those are the areas where we believe innovation is key. And that brings us to establishing the Critical Materials Innovation Hub, which was founded in 2013 as a result of the first wave of rare earth price increases that resulted from a geopolitical issue that developed between Japan and China in 2010. And so we were the first action taken by the US government to begin to address the supply chain. And at the beginning, it was mostly the rare earths. Our mission was to develop technologies to serve as an innovation pipeline to develop technologies to address the challenges that are faced by US manufacturers in establishing the supply chain for these critical materials. And we're going to do that by accelerating the rate of technology development. We're going to have to educate and create a workforce because they don't exist, because there's been no market for them. And we certainly want to create technologies that are de-risked, that industry would be willing to continue to invest in and advance from taking it out of the laboratory and trying to deploy that into our manufacturing. So we are charged with doing early stage applied research. And as I mentioned, we are a collaborative network of 9 national labs, 20 universities, and actually our number is more like 28 industry partners. And the 3 areas that we try to focus our attention are enhancing and diversifying the supply, so finding more efficient ways to recover the materials that we have, and unlocking new sources that are considered unconventional, meaning we may know how to get them out, but it's cost prohibitive, or there's other challenges, environmentally prohibitive. So those are considered unconventional sources. So enhancing and diversifying source or supply, that's the supply side. Action, we'll create more. Don't have enough, we'll create more. Developing substitutes, which is really addressing a demand side. So if I have the alternative to a permanent magnet, then I don't need as much rare earths to make those magnets if I can deploy an alternative. And then finally, building a circular economy, which is mostly about thinking about, can we be more efficient with our materials and manufacturing? Can we develop recycling methods that are environmentally sound? Can we develop manufacturing processes that generate less waste and minimize the use of the critical materials? All right. So one can think about innovation in kind of this linear fashion, where we start with maybe at the far left, Office of Science. So this is basically discovery science. So we try to understand the laws of chemistry and physics, and from there we can maybe understand magnetism, so we can think of new magnets, and then we go into early stage R&D, where we go in the lab and we try to make those magnets. So it's this linear progression from really basic science on the far left, and we do early stage R&D and then applied R&D, and then we do demonstrations that shows the feasibility. And I picked on materials, but it can be processes too. And then we go to large scale demonstrations and at scale deployment. Nice depiction of how technology can develop from the very, very discovery-based work in a laboratory to actual manufacturing. And yes, it kind of works this way, but it doesn't. But just to say, well, maybe here's an example of how it can work in this linear fashion. So this is a group we've funded through CMI. It started with some basic science. For those of you familiar with the rare earths, you may know that they all appear together. They're very chemically similar. That's how they got their name. They're rare because it was difficult to separate one from the other. And so there's a lot of work to understand how can we do that more efficiently. So new strategies for the separation of rare earths means really new chemicals that can exploit the differences between one rare earth from the next. And if you can develop that, as they did, that understanding, then you could increase the separation factor. So right now, separation factors for commercial are like 1.2. The number isn't necessarily important, except what it means is you need about 150 stages to purify one rare earth from its neighbor. You can imagine 150 stages occupying a facility that's maybe a football field in length, so a large-scale separation facility. And so it takes a lot of land, takes a lot of water, takes a lot of chemicals. And so if you can improve that separation factor by, say, a factor of 2 or 3, which this work has done, then you can reduce everything by a factor of 3. And that's a tremendous savings all around in capital equipment, in land use, in operational costs. And so that's certainly what we're trying to achieve. Develop a new thing that really make a difference, be transformative, be innovative. And so we were able to demonstrate that. And it worked really, really well in the laboratory. And then, of course, the next stage is to go to that larger demonstration. Well, now we need more than a few grams of this molecule, and we had to figure out how are we going to make kilograms of this material. And so the challenge changed from understanding the physics and chemistry to how do we synthesize the material in the quantities we need at the purity levels that are required. And that's been kind of the challenge that we're doing right now. So that kind of is an example of the linear process, but it really doesn't work that way, because as they created the larger quantities, they were really striving for high purity, which is what you do in the laboratory, right? I mean, you're trying to understand the basic physics and chemistry, so you want everything as pure as you can. Get it? Well, it turns out when you scale it and you try to do this on the kilogram scale, that high purity ended up gelling the system. And the last thing you want in a fluid-based system is to have gel formation. It turned out that they needed to have impure reagent. And those impurities kept the gelling from happening. So there was actually a loop that happened. So as they scaled the synthesis, they had to go back to the earlier stages of the R&D to understand why the gelling was occurring and what could lead to eliminating that problem. So it's not really linear. And so let me talk about innovation engines, because that's really what we're trying to do. We're trying to develop a material, or in this case, a process that has the right properties for improvement. That's supposed to be a for improvement. And so what I show there is a hysteresis curve for a magnet. It could have been this new ligand that I talked about, the new molecule. Certainly had the right properties. But we have to go farther than that. We just can't decide the chemistry is good, the performance is good, and life will be good. We have to figure out how those materials or processes can be made to work. Right? And that's the example of scaling the synthesis. How do we get to large quantities and still have it work? And then, oops. And then it doesn't stop there. Industry has to adopt it. If industry doesn't adopt it, then it's just an invention that's going to sit on the shelf. And it's not really an innovation because it hasn't changed anything. It's just an invention. And in order for industry to adopt new materials or new processes, there's all these other factors that have to be considered. For example, performance advantage. Of course, we want something always. We want something that works better. It's cheaper. Well, maybe the capital expenditures and the operational expenditures, you have to figure that out. Can they get the material, right? We came up with the new molecule, but now they need it in kilogram quantities. So there's a supply chain issue for this new chemical. The techno-economic analyses, are they able to regenerate the molecule after it's been used, or do they have to continually buy more? That's a huge factor Nobody wants to continue to buy more. That's an ongoing cost. Environmental impacts. If this new molecule was dangerous, what happens if it's released into our water, wastewater? Will it kill our microbial communities that treat our wastewater? What kind of implications are there? And then the last one, which seems to be covered by this thing, is social acceptance. And so is it going to be socially acceptable to use this? And that's a big factor. So in essence, well, all of those three things could be true. There we go. There's only the intersection of all three that actually can result in innovations that are worth pursuing. So really the keys to an effective innovation pipeline is more of a circular, because as the technology matures, you may have to go back into the laboratory. So you need a balanced integration between the science and the technology across TRL levels. TRL is technology readiness levels. It's a measure of how ready that technology is for deployment. TRLs go from 0 to 9, 0 being laboratory discovery science, 9 is production. So there's a way to measure this. You need to be able to have multidisciplinary teams. So yes, the molecule we developed was developed by chemists. Chemical engineers figure out how to make it, synthesize it in quantity. Mineral processors are the ones who ultimately will use it. So extractive metallurgists. So you need a multidisciplinary team that can stay together throughout the entire process, trying toward that common goal. And you need an effective, engaged industry partners, because in the end, while we can be very smart in our laboratory, our academic environments, or our national labs, in the end, it's industry that knows what works. What regulations? I'm no expert in EPA regulations. They know what works, and they have to be able to input into the R&D early and often at the earliest stages to be able to have technology that ultimately will be deployed. So let me give you an example. I don't know what my timing is here, but I want to talk about a sustainable value recovery from electronic wastes. As you all know, electronic waste, we all have it, right? I mean, we generate it, our laptops, our phones, and there's a multitude of materials in each of those. And so how can we actually get sustainable value recovery from electronic waste? For example, rare earths. In your phone, your speaker, your vibration is all magnets. Your screen has lanthanum oxide in it for UV protection. The red and green colors in your LEDs are rare earth-based materials. So wouldn't it be nice to pull those out and not just throw them into a landfill? And so we developed an acid-free dissolution recycling technology. And sounds really good, doesn't it? Sounds very sustainable, very green chemistry, and it is. It really is. But the question, of course, as I hope I've been able to say, how do you get it integrated into society in a way that actually will bring value? Because if it's not bringing value, no company's going to take this technology. In the end, that's the bottom line. All right, so there are many challenges to e-waste. It does require different considerations than, say, primary sources. And here what I mean by primary sources is mineral sources. So if I have an ore, it's really simple. I have ore, I have minerals that I want, and I have rock that I don't want. Take your phone. It's all valuable material. I have steel, I have gold in the circuit boards, I have aluminum, I have the rare earths, I have tantalum in the capacitors. There's a whole host of valuable things in your phone. So it's no longer just an either or, mineral versus rock. It's all of the above. How do I gain value from all of that? So it is different. Recycling is different. However, there isn't a lot of tantalum in your phones. There's very little rare earth, maybe 0.5%, which is not really a good ore when you think about it. So it's a dilute waste stream versus process intensification. So if it's a rich ore, like the rare earth mine in California, then you have processes and it's valuable. But here it's dilute. So how do you deal with a dilute waste stream? Which means you have to process lots of phones before you can accumulate enough value to make it happen. So the third bullet is this idea of integration. So we've developed this acid-free dissolution. That's really the product of the technology. It's to recover the rare earths. How do we get that deployed in a way that doesn't disrupt what we're already doing? In other words, we are recycling e-waste. We are recovering the gold and the copper and the aluminum and the steel. Because one, we know how to do that, and we can get enough of each of those to make it the value proposition. So now I come along with my new technology and I say, oh, well, now I can get the rare earths. But if it destroys what industry is already doing, then they're going to be reluctant. They're going to say, no, I don't want to do that. Or if it requires a whole new factory, I don't want to invest in that. So you have an uphill battle. You have a new technology, but it's got to make sense. It's got to be non-disruptive. It's got to be integrated into the value chain that already exists. The value proposition does depend on usually multiple companies in multiple regions. So, for example, you have people who collect e-waste, and they collect it and they sell it to reprocessors who then process it, and they sell their offtake to another company, the aluminum, the copper, the gold. So it's an ecosystem that you have to deal with. No one company typically cannot present the full value. And then for it to be sustainable, it does require a little bit of sustainable technologies, and acid-free is one aspect of that, but regeneration of chemicals, minimizing the waste, all of that comes into play. So it's not just say the acid-free, but it's the fact that the water can be recirculated, it's not going down the drain. Everything else that you can recover that has value is being recovered. And so, yeah. So let's talk magnets, because that's really what this technology is focused on. Magnets are interesting. There are different types of magnets, rare earth magnets. They're in most of your devices. And the way that you use magnets is that the way magnets are sourced depends on the application and the temperature. So the higher the temperature, the more dysprosium you need. So dysprosium is one of the rare earths that is added to the neodymium permanent magnets that increases the performance at temperature. So the most demanding applications, 200C, 220, you might have as much as 10% dysprosium. Turns out dysprosium is really hard to come by. The Chinese import it. We have Mountain Pass Mine in California. They have 0% dysprosium. So if you want to think about recycling the rare earths and the magnets, dysprosium is the high value item. It's about 10 times more, has a 10 times greater value than neodymium, which is the bulk of the magnet. And clearly it could have up to 10%. So it's what you got to target. You got to come up with a process to do that. And so acid-free dissolution was developed. Why acid-free? Well, you can use acid, and the magnets just dissolve quickly and lots of bubbles. But the gold and the copper and the steel and the aluminum also all dissolves. So now you get this liquid that has everything in it. You have to separate it. That's difficult. But more importantly, you've taken all the gold and the copper from what's already being processed. So why would, if I'm a reprocessor, why would I want to use acid? Because now I've just taken what I'm making money on and I put it into solution, and now I got to spend money to get it back out. So this acid-free actually can pull out 99.5% pure rare earth elements. It's applicable to different feedstocks, and we'll show you that it's going to be used for hard drives. Selective leaching, it only attacks the rare earths, leaving everything else the same. So nobody's losing any value. So, and as a result, it has a favorable economic analysis. Operationally, it's safe and environmentally benign. It's a copper salt. Many of you may have had this, at least I did in my chemistry set when I was 10. Copper sulfate is a nice simple salt, and it does the trick. I wouldn't drink it, but it's safe. Life is good. And because it's copper, actually, in the way this works, it puts copper into the scrap, making it more valuable for the reprocessor. Bonus, increased value. And so, and then it has valuable byproducts. And so all good things. So why hard drives? Why do we focus on hard drives? Because the data centers have a tremendous number of hard drives in every data center, and they turn over on the order of 50 to 75,000 hard drives every month. They're all in one space, so you don't have to go and collect your phone and your phone and your phone. They're all in one location, and they are shredded. They're shredded at the location to protect your data. So it's already ready to be processed. And so you take that e-waste, that shredded hard drive, and you throw it into this solution, and literally before your eyes, you can watch it. It dissolves the rare earths in a relatively short period of time. And the shred remains intact. It goes on to the reprocessors. They recover their value, maybe a little bit more with the copper. And what you end up is getting mixed rare earth oxide. You get the neodymium and the dysprosium, which you can then separate into individual oxides. You can turn those oxides back to metal, and that metal can then be turned back into magnets and start the whole process. Looks like a nice circular economy, doesn't it? Not always that simple, but it's very nice. So I told you our mission was to accelerate the development. This is actually pretty quick. It only goes through 2022. I can fill in the next 3 years, but it was only discovered in 2016. It was kind of, the next couple of years was laboratory work, followed by some mid-scale activities with some additional funding, STTR, startup factory, lots of help here in taking it from the lab-based on the lower left to something that's obviously you're moving a carton full of shred around with a forklift. So it's scaled at the end of 2022. The technology was licensed. They've got the first commercial rare earth metal production from this process. They have now scaled this even further to pilot scale, and I believe their projection is 45,000 tons to be processed of hard drives to be processed on an annual basis. So we are doing it. We are recovering our rare earths. And they, yeah. So in addition to the metal, which is important for making magnets to get it back into kind of the circular, there are other things that can come out. So not all magnets are created the same. There are samarium magnets from samarium cobalt that can get mixed in. Sometimes you don't know that they're there. But you can pull out the samarium cobalt out of those magnets and produce oxides or sulfates or phosphates. Note the indigo blue for dye. So there's all kinds of products you can pull out. You can even precipitate out any remaining copper and turn it as copper metal, all of which has value. So it really is important to look at the entire process, what can be your products, what has value, and be able to kind of holistically see that this process can be sustainable because you have multiple ways to produce products for sale. All right, and just be sure if you take that metal and you turn it back into a magnet, then you can get the magnetic properties of the original material that you dissolved. So that's an important part, that being able to demonstrate that you can make the magnets from the recovered rare earths. So as I mentioned, it's been scaled and scaled in 2022. That rare earth, that's about a kilogram of rare earth metal that was produced by this process. All right. Sustainability, though. So the question becomes, what are the impacts? If we were to put this technology into place and we were going to recover the dysprosium, will it be better than trying to produce dysprosium from primary or virgin rare earth production? And so you can do life cycle analyses, and on the left of this diagram are a bunch of impacts: ozone depletion, global warming, smog, and so on. And you can compare the two. If I make dysprosium by recycling versus dysprosium from mineral sources. And for the most part, everything's improved. The one area that was first flagged by the initial analysis was actually the production of copper nitrate, which I said we use copper sulfate, and that's why we use copper sulfate, because the copper nitrate had a high ecotoxicity. So they shifted and they went to copper sulfate. It works just as well, and it eliminates that contribution, not just for ecotoxicity, but in fact, it eliminated contributions to all the impact categories. Again, that's still not enough, because I told you got to have multiple industries, right? And so now we've got a company that can do the acid-free dissolution, but you got to ask, where are they going to get their feedstock? So you got to start making arrangements with recyclers, with data centers, the Microsofts of the world, with magnet manufacturers for their waste. So you've got a bunch of companies and intake agreements you have to establish just to be able to feed the technology. And then, of course, whether you're producing metals or salts, oxides, oxalates, or any of the other wonderful things that this process can do, you need offtake partners. And until you complete that, the intake and the offtake, you're really not in a position to claim that you've innovated. Fortunately, this company has done so, and this is one of our proud innovations from CMI. So I think that that kind of wraps up what I wanted to say, and I'm happy to answer questions following the breakout sessions, right?
Okay, so that brings us to our 5-minute discussion. We have the discussion prompts on the slides here, and we'll also have them in our breakout room. RJ will open the breakout room for those online. If you're a student in remote, please join the breakout room. If you're just also a visitor here, you may join the breakout room online. You're welcome to do so. We encourage you to do so, and we'll continue with a Q&A in 5 minutes. And in the classroom, please start your discussions. Okay, so it is now time to get back here. Those online, if you have questions online, please write them into the chat. RJ will sort them through, and we will have your questions answered also. But we'll start here in the room. Please get your questions ready, and whoever likes to raise their hand first may do so. Yes, please, over here. Please repeat the question.
Okay, I actually wrote this one down so I can articulate it properly. Kind of longer, I apologize. What is the intent of the IP created by the various national laboratories? On one hand, making something open source may greatly further the pursuit of clean energy and net zero, while keeping it patented or licensed may increase competitiveness between the United States and China for prioritizing national defense. How are these seemingly negatively correlated priorities balanced by the DOE?
Let's see if I could even try to repeat that. That's very, very well articulated. So maybe I'll try to paraphrase. So your question is, how does the IP that's generated in the hub, how is that protected? How does that provide protection to the US versus China? Versus the more maybe open source approach of giving everyone an opportunity to practice some of this new technology, right? Yep. Because it's better for everyone. Yeah. So interestingly, it's not a simple answer. It never is. You want to protect your IP. Well, one, it's an expectation of the funding. We are using your taxpayer dollars, so we want to make sure that the benefit of any technology we develop is available to the United States and first and foremost.
Maybe I can tailor it one more time. So is the funding, whenever funding is granted for a project, is it kind of determined right there whether or not the IP is going to be open source or whether it's protected? Or is it kind of like after this development's been happening, we realize what the value of this IP is, then we make it? Or is it kind of like that?
So, no, in general, if you receive government funding, they're going to expect you to protect any IP that you develop under that funding. Whether that IP, the invention, actually is suitable for patenting is often given to tech transfer offices. There are costs associated with patenting, and there are costs both domestically and for foreign filing. Unfortunately, there is a business decision to be made as to whether or not the tech transfer offices will expend those dollars to do that protection. So if it is patented, the first thing that happens to a patent is it's publicly disseminated at the USPTO office, right? So we're not really hiding it from anyone. I think what's missed often is while the initial, and I'll pick on ADR, while the initial patent was filed and it's been licensed by this company, the actual process they practice today is more governed by know-how, possibly trade secrets, than it is by that original patent. Most companies won't continue to patent beyond the initial because the competitive edge is by the know-how. And so, so on the one hand, yes, government funding requires you to follow that IP route and not do open source, although software and other things can be open source. But in the end, an industry is going to protect its competitive edge by not revealing what amounts to is manufacturing know-how. Yeah.
I've got a question on ADR. It's kind of a two-part question. You mentioned that the technology is expected to process around 45,000 tons. And I'm wondering how much of that 40,000 tons is relative to the e-waste of the United States. And I'm also curious about how efficient the technology is. Like, is it using 100% of, is it recovering 100% of materials that we're looking to recover?
So the question is about the ADR process, and the first, it's a two-part question. The first part is for this company that is developing the pilot scale at 4,000 to 5,000 ton per year, how much does that quantity represent or is representative of the entire e-waste? So it's a small percentage. I don't have a number for you. We generate a lot of electronic waste. But please note that the company has not targeted all electronic waste. They've targeted a very specific type of electronic waste, and that's hard drive from data centers. And the reason they do that is because the collection issue is not a part of their economic analyses, right? The other thing that they've been able to do is rather than ship the entire shred from location to location, they do some pre-sorting at the original location. So they're only shipping the part that can be recovered. The second part, if I got this right, is does the ADR recover all of the material that the original technology was intended to recover? The answer is yes. So the intent of the ADR technology was to recover, to dissolve and leach out the rare earths from the magnets. And it does so with 99.5% efficiency. No, I'm sorry. Plus 95% efficiency. And what's recovered is 99.5% pure.
I got my second, I think.
So you guys can do that technique to like rare earth metals that are alloyed inside other metals and still get that same recovery?
So the question is can the ADR method leach out, dissolve the rare earths, even though it might be contained in another alloy, the rare earths in another alloy? In general, I think the answer is yes. It depends on really the alloy. So we've focused on magnets. Magnets are roughly 30% rare earth, the remainder essentially iron. And the process does rely on the iron being a part of the process. So the copper is being reduced, so it's going from an oxidative state to metal. And the iron is being oxidized from a metallic state to something probably a ferrous iron. And so in the process, it liberates the rare earth, and that's what gets dissolved. So could that work for others? So other alloys or compounds that contain rare earths? Yes, it can. And remember, the rare earths are fairly reactive elements. And so they're really prone to wanting to go into solution.
My question is sort of like tying 4.3 to your mission statement and the right repair method, right? And so do you think, can we meet recycling? Can we meet growing demand for recycling if we had laws like framed the same way as the right affairs where manufacturers are on board with the way they design technology better process.
Let me see if I can repeat the question. So the question is more of a policy question. Can we initiate policies that require the manufacturers to design for recycling? And if they did so, could they meet the growing demand for these minerals and materials, because the ease of recycling would be easier. The ease of recycling would be enhanced, and we should be able to recover more. Hopefully I got that question fairly close. Okay. So recycling is an interesting thing in the sense that what we are recycling today are products that are made 10 to 15 years ago. So an electric vehicle, the first Priuses are coming back, they're reaching end of life. And in those, you have electric motors that have magnets that have very high dysprosium contents. You also have batteries that are not lithium ion based. They are nickel metal hydrides, or if they are lithium ion, they're probably heavy cobalt containing batteries. So we can recover those. But the chemistries have changed now. Our batteries contain less cobalt because they're because of the cost. They are now switching over to LFP, lithium iron phosphates. So to meet the growing demand, one has to adjust that demand for the changes in technology. So let's just let's go to the extreme of, for some reason, we're just going to abandon lithium cobalt, NMCs, nickel manganese cobalt batteries, chemistries, and let's go for lithium iron phosphates. Why recycle what's already out there? We have no need for the cobalt, nickel, or manganese. We could do the lithium, but lithium doesn't carry a lot of value. It's the cobalt and nickel that carries the value for recycling. So there's complexities that can come into play here. In general, you cannot meet a growing demand through recycling. Think of it this way. If the car companies made 50,000 electric vehicles exactly the same way 10 years ago, then there's 50,000 to be recovered. But if they're now making 200,000, those 50,000 that you could recover, recycle today from 10 years ago, could only supply, if they're 100% recycled, no loss, they could only make 50,000 cars. So if you want to make 100 or 200,000, you're going to have to mine more. So a growing demand scenario is one that I think the projections are you can meet 25 to 30% of your growing demand. Of course, that depends on your predictions of what that demand and how it's going to grow. Now, I will draw a nuance with dysprosium. There isn't dysprosium readily available from primary sources. So recovering the dysprosium from the magnets may be able to feed our need to make the high demand application magnets. Only because 10 years ago, we were making magnets with high levels of dysprosium. Today, we can reduce but we have new technology that reduces the amount of dysprosium for a given magnet, and we can still get the same performance as if it had more dysprosium. So if we recover the dysprosium from 10 years ago and say it's 10%, and now we're making magnets at 1%, then we could probably make 10 magnets for one recovered. So I don't think giving or mandating manufacturers to either design for recycle would necessarily help. Nor, although it might, I'll give you an example. Currently, electric vehicles are being brought to salvage yards, right? The vehicle salvage industry is a for-profit industry. We've been recycling cars for a long time. The battery pack in an electric vehicle takes some doing to remove, right? They're big, they're heavy, they're charged, they have to be discharged. But on the aftermarket, they'll bring about $1,000. And that's not bad. That's a pretty good price. And so it's worth dismantling that technology, I mean that EV for the battery pack. An electric motor on that same vehicle will have resale for less than $100. Now you're the salvage yard manager and you're going to say, well, do I devote time and effort to remove that from the vehicle, assuming you had some place you could sell it that would then take out the copper, take out the steel, the magnets, and recycle all those things? Or do I leave it in the car, because I'm only going to get $100, and just shred the motor with the rest of the vehicle, because that's what they do. And then they worry about separating the copper. They're more likely to do the latter. And so, so it's not clear to me how much we should regulate the ability to recover, right? Lead acid batteries, 99% are recycled. But there's a reason for that, right? Because of the lead. Motors aren't going to get the same sort of attention because they lack the toxicity. So it really is a complicated issue. Maybe rambled on with this answer, but it's because there are all these different factors that come into play. So I hope I answered your question.
Okay. Is ADR being applied to other like e-waste sources besides hard drives? Because I understand like there's like large concentrations of hard drives and it's easier to source it, but like, do you think there'd be other sources of that?
Yes. And so there currently is a program that the company and the researchers are involved in that are considering what it would take to recycle from just general e-waste. Now, hard drives only have like a 0.5% rare earths in it. I suspect our phones have even less. And so, but it's about a regional effort. Can you deploy the technology in a way that economically makes sense? So, you know, I talked about how the hard drives are at a location, they're shredded, they're now sorted, and they're only shipping the magnet containing material and none of the other stuff. That certainly is one model for deploying this technology. The other model is to develop a modular reactor that could be taken to the collection point for the other e-waste. And you could kind of franchise that, right? You could say to the recycler, the collector, to, you know, if you would run all your e-waste through our solution, then we could get the rare earths and we'll precipitate them and ship us the precipitate. So that's a different business model altogether, because now it's modular and you could deploy it on a regional basis. But those are the types of things that you have to think about, is how does it fit? Again, how do you integrate this technology into a different a feedstock? Because that feedstock has a different route. It's not the same as what's happening with hard drives. And so the hard drives was the easy one. And that's why they went there. Yeah. Does that? Yeah.
So thank you to all who asked questions. Thank you for our visitors from Kyushu University for coming. You are welcome to stay with us throughout the semester, but I guess you will probably have to travel back. We wish you a good time here in Boise and a safe travel back to Kyushu. So thank you for visiting. And with this, we end. Let's give another round of applause and a thank you to Dr. Lograsso.